So today I want to talk about what is a variational autoencoder, which is an autoencoder but with a little bit of extra steps. Specifically in this video, I want to talk about some introduction to autoencoder and variational autoencoder. And next, I want to talk about advantages and disadvantages of VAE. And I want to follow that up with a simple R workshop with MNIST data and how we can use VAE architecture to actually reproduce the handwritings in MNIST and in some way make it actually better. And the last one, I want to talk about two examples of VAE in research and how people has been using VAE in the last 2-3 years and so on. So first thing was, what is an autoencoder? So autoencoder is a special type of neural network that trains to copy its input to its output. So in this example, given an image of a handwriting digits, the autoencoder compressed the image into a lower dimensional latent representation. So in this case, we're compressing like 28 times 28 pixel down to maybe 2 pixel. And then we can decompress that 2 pixel back to a single image. So an autoencoder tries to compress the data while preserving all the information with it and actually understand that, minimizing the construction error. So you can actually have a very good, what is that called, a run through of what is autoencoder in this introduction, where we can actually, for example, some basic autoencoder on how we can have an original image and we can reconstruct it back. And we can actually add something into that autoencoder to actually do some image denoising, because noise are fundamentally information that cannot be compressed. So when we actually compress images, we actually get those noises actually get filtered out of it. So you actually get a clearer image using reconstruction of image using an autoencoder. Okay, so these are all nice and easy and stuff, but the thing about that is usually it overfits what it is, right? So because you're compressing the data has to be very close to what you give it to be. So the decoder, when you generate the image are incredibly similar to what you fit it in. So this is a problem when you want to create an image that you do not fit it in. For example, I want to create an image between like a pants and a shirt, or a pants and a shoe, or somewhere in between the two. The autoencoder will not be able to do that for you. It doesn't understand. So the separation, so this 10 image should be separate into very fast spaces with no overlap in between. So what they try to do in this case is to try to add some noise into the middle of the bottleneck layer so that it has a little bit more general representation in that bottleneck layer. In a terminology, we call it the regularization of the latent variables. Okay, so the variational autoencoder is basically a probabilistic take on the autoencoder, which take the high dimensional data and compress into smaller representation, which is the same, but unlike the autoencoder, which map the input into a latent vector, which is like 2 numbers, a VAE maps the input data into parameters of probability distribution, such as the mean and variance of a Gaussian distribution. So this approach produces a continuous structured latent space, which is useful for not just image generation, but for a little bit more general approach on how the data is actually stored. Okay, so actually, I'm not going to talk too much about the means and variance of Gaussian random variable and how it is being calculated and back propagated as a value, because I saw one on Stack Exchange over here, and these are the total number of equations that you have to do just to get a value out. So I'm not going to go into, because most of the programming will actually help with that. But what you basically need to understand is, compared to the autoencoder we talked about before, the bottleneck layer has 2 things. So instead of like 2 numbers in the bottleneck layer, they will store things as 2 different things. First one is the mean, and another one is the variance and standard deviation of the probability distribution. So you can think of it like mean and just because you are feeding in the mean with a standard deviation of 1 doesn't mean it will always give you a 1. So sometimes it give you a 1, sometimes it give you a 2, sometimes it give you 1.5, and then so on and so forth. So the learning parameters is going to be really, really general, so that when they compress this data down, they need to understand how to actually make it so that it doesn't overfit the data. That's the principle of a variational autoencoder. So like something like what I just said, where instead of storing the data as 3.5, 6.5, 7.1, 1.12, in the normal autoencoder, the VAE will actually store it as a mean as 4.1, STR 1.3, and a win by 1.6 and STR 0.5. And we actually use that function to actually recalculate our latent vectors and use that latent vector into our decoder. So that's basically it. So it's just another layer into the network basically. So again, I'm not going to talk about the loss function and the chaos divergence because it's very, very mathematic based. So actually, let's go to our example in R. But before that, I want to just talk through what does the logic and the concept behind it. We have MNIST data, which is 60,000 handwritten digits. Each of them is 28 times 28 pixel in black and white. So what we're going to do is actually build three things. We're going to build an encoder, a decoder, and a generator. So you'll see the architecture later. So we'll train the encoder and decoder as input and output on the neural network, and we're going to use our generator to actually generate the output. So we should be able to reconstruct something like that in MNIST, and we should be able to do it slightly better than the autoencoder. So let's actually just go to R before we skip forward with the advantages there. Okay, so this is the R code to actually run the whole thing. I actually take it directly from the Keras R Studio, and it actually works on the old TensorFlow version, but they added this so that it works on TensorFlow like 2.0 and above. So I'm running 2.9. So if you're newer than mine, it should also work. So this code can be downloaded from my GitHub page, or if you don't want to do that, you can also download directly from the website, the original website here. Just I added a little bit more modularization to the code that they provided. So the first thing, of course, is to load in the library. So this one actually just make the compatibility of the code to make it compatible with version 1.9 and before. So this is coded on TensorFlow version 1. So if you're running version 2 of TensorFlow, you have to run this line, otherwise it will not work. Okay, so once you've done that, they actually have some parameter that is predetermined. So why they usually do that is that everything below is going to be written as a function. So if you have your parameter predetermined, you can actually very easily change, for example, the original dimension as 256, and you can actually just code whatever that is down there directly. So it's a lot easier to run loops. For example, try different parameters in your network if you predefine them. So that's basically what it is. If you don't want to do that, that's fine as well. So the first thing is to actually understand the data and to prepare the data for us to run. So we're going to use a dataset in MNIST that's just going to be readily available once you load in the library. And we're going to print the first one that we have. So the parameters, because they're stored in they're image in black and white. So they're stored in value on 0 to 255. Okay. So what you see is if it's a 253, it's going to be a very bright white point. If it's a 0, it's going to be a black point. But it is really hard to see like that, which is why we're going to run a p-heat map on it, which will actually print us the black and white. So in this case, the first value inside that we printed out is a 5. You can also try different value, for example, the AD value, and we can actually try to see what value it is. Yeah, so it's a 7 and so forth. Okay. So what we need to do next for the data preparation is to actually divide them by 255 because they're represented in 255. We want to narrow it down to 0 and 1 because neural network tends to like that a little bit better. And we're going to reshape the 28 and 28 pixel that we see just now. So we're going to reshape the square into a line. So we flatten it out so that we can fit it into our neural network later directly. So we're not running any convolutional neural network. If you want to run a CNN on it, then you cannot do such reshape because it will not work. But in this case, the single dimension of it actually works well for the V8. Okay, so which is why we have flattened it out to 284 different value, because that's 28 times 28. So the input will be 784 numbers in this case. Okay, so we also have 60,000 number. Each of them is 784 wide. Which of them is a 784 wide vectors. So next one is the confusing part, where we are doing the model definition and structure. So unlike usually we just stack them in layer because they're MLP, very straightforward. This one we have to define them separately because we're gonna use them separately later. So the first one is the encoder, and these are the name of the encoder. So we have three main layers. X is we have an input layer which fit into X and fit into H, and then H will fit into the bottleneck layer, in this case the mean and the z-log variable. So z-log variable is the standard deviation that we talked about just now. And then we actually have to join these two layers into a new layer called concatenate. And then we're going to use that concatenate layer, which is like 4 numbers. So yeah, z-mean is, so we have two bottleneck layer. So we have 2 means and 2 standard deviation. So we join them into a new layer with 4 numbers. And we're going to use the first 2 number to generate a new mean. And we're going to use the last 2 mean and variable to actually generate a new a latent variable in this case. Okay, so that will become what we call a lambda. So that will be the lambda that will fit into our decoder. Okay, so from that on, it's actually pretty straightforward. We have a decoder and generator, which is fundamentally the same thing, just that they're phrased slightly differently so that the output can be, so it's easier on the later process. I'll show you how, but you need to understand this wording that they use because it's kind of confusing. So X is actually simply a layer input with the original dimension of the shape, which is 784. And we're gonna connect X to a second layer with this. Okay, can you see there's adding another layer of after X with the intermediate dimension as the number of nodes. So in this case, the intermediate layer has 256. So it's L because it's an integral. So if you don't have L, it becomes a decimal. You put an L in the back, it becomes an integral. It becomes a numeric, means 1, 2, 3, 4, my whole number. So it's easier to define. So we are defining a second layer here with 256 nodes with an activation of a ReLU. So you do not have to define the first layer because they are the input layer. So you don't need activation function for that. And then the second layer will be connected to the Z mean and Z log var so that we get like 2 here and then 2 here. So you can actually change the number of latent vector, the latent variable here to 4, 5, 6, 7, depends on your depends on how many do you think you need. We're just compress it to 2, so it should be enough for this case. So we're compressing 784 numbers into 2 numbers and out again. So when I made 2 numbers is 2 means and 2 standard deviation, something like that. Okay, so the next one is how do we calculate the final latent variable based on the means and the standard variation, and ST. Okay, so not going to go inside, but basically you can see that the mean is being added. So the mean is being added with a little bit of noise so that it's not a fixed variable. So every time you train, the variable gonna change a little bit here and there, here and there, here and there, here and there, so it doesn't overfit the data. That's basically what sampling actually means right here. Okay, so Z means is the actual bottleneck layer, which will be actually fit into our decoder later. So the decoder, very straightforward. It's just that, oh yeah, this is the one that I'm talking about, where we fix the Z, which is actually just joining the Z mean and Z variable. We do a lambda on it and we actually fit it back in. So Z layer will be the mean that we actually be going to fit into a next one. Okay, so once we've done that, we just do the reverse of our encoder, which is the decoder. We have the intermediate dimension with the ReLU, similar to what we did just now. And then we have another sigmoid on the output layer with the decoder mean right here. Okay, so the Z is going to be coded into H encoded, and the decoder mean is going to be like the H is going to be connected to the X encoded mean. Yeah, the name is very confusing, but what we can do is just I have not run this, isn't it? Yeah, let's run this, and once we run the next one, easily we can actually see from the summary what I meant. So you can see that from the input layer of 784, we connect to a dense layer of 256, and the dense layer connected to the mean and the log variable, and then we concatenate these two into a new layer right here, and then using our function of sampling, we actually do we run the concatenate layer into a new bottleneck layer called lambda, and then from the lambda we're going to use a decoder of dense 3 and dense 4 so that we can actually recreate our drawings basically. Okay, so you can actually think of it as these two will be our generator like that. Okay, so how do we actually calculate the losses is also a lot more complicated because we cannot just run a simple z-mean square, but basically it's just a custom function though that it's so that it can actually calculate the losses properly, because we don't calculate the losses directly from the input and the output, but the way of calculating is slightly different because of the functions and noise and stuff like that. So I'm not going to go deep into the mathematics, but you need to understand that the losses calculated based on something in the middle, which is why you can find there's a z-mean right here. Okay, yeah, but the concept itself is the same. We're just calculating so that the input match the output. Okay, so once we've done that, we're going to use RMS rule mean square propagation and stuff like that, and we're going to do a normal fitting of using X train as an input and X train as an output. So it's training on itself, just that unlike the autoencoder, that a little bit more step in the middle, and the loss function is a little bit different. Okay, so just to make sure that we are not crazy, we're also going to do a validation data on our testing, which I believe ACT-test has about, yeah, how many of them are there? So training has 60,000. I think the test is about 20,000 digits, so that if you see the loss and variation loss are very similar to one another, most likely your neural network should work quite fine. However, if your validation loss is off the chart, means you might need to retrain your parameters by changing, for example, the batch size, the number of neurons, number of nodes in the middle. Here and there, there's a lot more things that you can change. So the other thing about running a neural network in this case is it should converge quite fast in the first 5 to 10 epoch. So if it doesn't, you might also need to adjust your parameter a little bit, so it doesn't show like a curve like this down and it just constantly go for a flat line. Usually it goes a simple route on a local minima where you just put everything at 0 because it's just easier, and you just stop there and doesn't want to do anything. So again, adjust the parameter. There's no correct way to do it. It depends on the data of your input. It depends on the thing. You might also want to look at your data. Maybe it's too noisy. So one of the greatest quote that I actually heard is that most of the good neural network are not because they have a good architecture, but rather that they just have good data. So data is actually more important than how do you do your coding. Okay, so it's just going to be training on 50 epoch, which is a pretty small amount, which is kind of intentional because we do not want it to overfit. That's the whole concept of VAE. So once we have the whole training done, what we're going to do is actually just, okay, so predict here is not using correctly. So what we do is we're going to feed our testing data into our encoder so that we can get our two-dimensional something like the two-dimensional latent vector. So in this case, you can actually have a look. They're just like that. So there's 10,000 digits input. Each of the digit get actually encoded to these two, what is that called, latent vectors, right? So these two latent vectors is a result of our standard mean and deviation, the resulted from the mean and deviation that we calculated just now. So it's already being calculated inside here. Okay, so it's usually run like a digipoint over here just to show that we have classified them properly, and if there are any kind of overlap between the samples that we have. So we can see the purple one and the pink one. I think it's 7 and 8 right here actually overlapping significantly, so that when we generate the data, we might find some problem separating a 7 from 8 when they might actually created something in the middle. So we might want to train it further, or again adjust it a little bit here and there. But so far everything else is separating nicely, and we're going to proceed from there. Okay, so let's just print a single number over here. So the input is slightly different because there will need actually 2 input for it to run, because remember every latent variables is a latent vectors has 2 variable. So if we just run the input here, so we can actually have an input of 0. So minus 2.1 is minus 1.6, and we can fit it into our predict using the generator, and we can actually plot them out. Whoops, object D not found. Actually, let's just run it again. Yep. So we can see that if we run our latent vector right, if we use the input of, where's my input? Input here of minus 2.2 and 1.4, we get a number 3, which is, which disappears. So we can run it again and again and again, because I'm using a run if over here as a random generator. So every time you run, it's going to generate like a different number. As you can see, this is on really high resolution. You can see individual pixel. You can still make it out. Yeah, this is a 6. This is a 8, and this is a 9. So it's pretty close to what is being fed in, and it's actually generating quite well. So again, you can actually run a lot of them to understand how it generates. So this is what the last one actually do. So what they do is they want a figure with 15 by 15, but I don't think it's enough. So I changed to 35 with a digit size of 28. That's like the megapixel of it. So yeah, that's the pixel of each of the generated output. So what they do is they write functions to automatically generate 35 times 35 different image with this loop, and they try to plot it out as a new image, which we can see it should come out soon. Yeah, everything is a lot slower when you are also screen recording. Yeah, so here let's just actually zoom in a little bit. So you can see that these are, when you fit in like all the different parameters, in this case I'm fitting in minus 3 to 3. Minus 4 to 4 of the latent variable. As you can see that it generates 0, like 6 and 1 and 3 and 8 and 9 and 2. So you can see that 0 to 9 should exist in this space nicely, and you can see the transition between each of the number. That's the interesting part. Can you see how the 0 slowly transition to 6 and slowly transition to 9? So this is where VAE is super useful, and autoencoder should not be able to do this. Okay, so that's the basic R code on all of it. So that's just the theory. So what it actually used in is a lot of different things. So I'm just going to talk about two, but VAE is an incredibly widespread use for generator. So we have previously talked about the advantage and disadvantages, which I don't like to talk about because it's not fair to compare VAE to autoencoder, because autoencoder is simply like a dimensional reduction a dimensional reduction tool, or like a data compression tool, while VAE serve more like a generation tool, right, for you to generate different things. So we added that. So in compared to autoencoder, it added a regularization coefficient that controls the influence. It gives signal control of how we want to model on latent distribution. Not super relevant. But compared to GAN are usually, okay, GAN is a generative adversarial network. So GAN is very useful to generate things that interpolating of data, while VAE is better to generating that kind of like extrapolation of data. Oversimplification, I know, but based on the data here from Grover 2008, GAN can generate image of high subjective perpetual quality, but they tend to lack support over the data, while VAE can generate more dispersed sample, better density model in terms of likelihood of criteria, which in a very small amount of input, VAE usually works better, right? So this is where bring us to our first example, where they use for medical image analysis. So in this case, this is in University of North Carolina, Chapel Hill. So what they do is actually using MRI and CT images. So for people that never work with MRI and CT images, they are super high dimensional data, right? They are scanning the patient like slice by slice and combine them together. There are also all the different like shine point. I don't know. I don't pretend to understand as well, but it's a really difficult and complicated data to understand. For example, the brain scan and situation, we don't, so only very certified people is able to read the brain scan and give you a verdict of whether it is a brain tumor or depression and so on. So what they're doing is actually trying to do kind of a classification situation on the brain model as well as the generation of it. Okay, so what they do is that they take a bunch of brain image, they throw it into a VAE, and they try to classify them on the different what is that called, different characteristic of the brain scan, and actually try to generate and then see how does it change from one to another. And they can actually, so what they have found is that the relationship between visual cues and clinical parameter HMSSE and CDR, they can easily figure out the relationship between important visual cue and 3 clinical parameters. So you have helped them significantly, not just to understand the classification of the patient, but also to generate more medical image so that they can make, perhaps what I would do is actually just make a caricature of those images. So just makes those conditions incredibly big so that we can actually see better the difference. For example, as a learning tool, you want people to be able to identify things, and I believe there's also a little bit more on like privacy situation. And that'll be a good one. So education, generate image for textbooks and stuff so that you don't have to, so that you can put out a very clean, very easy to understand image example for students. And you can also just release it without concerning the privacy of those patients in mind and so on. So the second one is for generation of antimicrobial peptide, which is another one that I found incredibly novel and good way of doing this. Again, I am not an expert in MRI or in antimicrobial peptides, but these are the 2 examples that I find interesting. So what they do in this case is to use protein model. So protein model in 3D space, you have like XYZ dimension, you have the type of proteins, you have the interaction, hydrophobicity, and all the different bonds connection and so on. So again, it's a super high dimensional data, and they just take those high dimensional data, which is like all those antimicrobial peptide data, take superdimensional, throw it into a VAE, and then try to regenerate of it. Okay, so what they intend to do is they're able to generate what are the peptide that should be also antimicrobial just by looking at how it is being encoded and how they're being decoded. So we can do, like in this case, perhaps just feature extractions and all the other stuff. They're all in the paper, which I'm gonna put this 2 link in the video description down below, so you can read how the author actually do it yourself. But basically, using VAE, they're able to better understanding the data. They can generate extra images for those data. In this case, they're able to understand some of the protein characteristic that leads to antimicrobial properties, as well as how to actually synthesize and make new proteins based on the model and the way of how they do it. So last one, just summarization of what we have learned about variational autoencoder is basically an autoencoder with a probabilistic distribution as its latent vector. Yeah, it shouldn't be a latent vector, it's just in the middle of the bottleneck layer. Okay, so it can provide more realistic output than an encoder compared to traditional AE. Whether they are better than GAN depends on the situation, but it's much better than normal autoencoder, right? It works more like a GAN. GAN is its data generation properties, and I don't think we should compare VAE to AE. It's not fair. And the last one, it can be used for image, 3D model, and all the other stuff that you can think of with high dimensional data. So right, it can compress like high dimensional data, compress it to a latent space, and regenerate those high dimensional data with like critical, what is that called? Critical characteristic that you want within those data, just like how we show with our MNIST data set just now with all the different parameters. Okay, so my voice is going away. So this is my video about variational autoencoder. Again, I do not claim to be an expert in all this thing. If I say anything wrongly, please just comment in the video description down below or anything. Or if you have any question, leave it in the comment down below as well. Liking the video would be great, but it's already 29 minutes. I'm not going to babble any further. Thank you for watching, and I will see you in the next video. Bye.